So let's return to the gas exchange regions and examine external respiration. Now, external respiration is the process of gas exchange between the air in the alveoli and the red blood cells that are in the bloodstream. So there are three factors that affect external respiration. We see that the first is the partial pressure gradients of the respiratory gases that are diffusing. We also see that the second one is the thickness of the respiratory membrane. And the third is a factor that's referred to as ventilation-perfusion coupling. So we will examine the partial pressure gradients first and return to the others later. So the term partial pressures is described with a law that's referred to as Dalton's law. And Dalton's law simply states that a total pressure of a mixture of gases is equal to the sum of the partial pressures of each gas within that mixture. So let's further break this down and see what Dalton's law is really telling us. So we'll start by examining Earth's atmosphere. So Earth's atmosphere is a mixture of gases, and Dalton's law applies to our atmospheric gases because Dalton's law describes the total pressure of a gas being equal to the sum of the partial pressures of the mixture of gases, and therefore has very huge implications for the diffusion of respiratory gases like oxygen. The two primary gases that compose Earth's atmosphere are nitrogen, which is shown as N2 on this figure here, and oxygen, which is shown as O2 on this figure. Nitrogen gas composes the majority of the atmosphere at 78.6%. However, our bodies do not use nitrogen gas in any way. So the gas that is important to us is oxygen. It composes 20.9% of the Earth's atmosphere. So now that we know the percentages of the relevant gases in the atmosphere, we can use those percentages to calculate the partial pressure of that gas. So both oxygen and carbon dioxide are our most important respiratory gases, so we'll focus on those. So at sea level, the total atmospheric pressure is 760 millimeters of mercury. So recall that the total atmospheric pressure is created by the mixture of gases in the atmosphere. The pressure is due to the weight of all of those gases sitting on top of you. So if we would like to calculate the partial pressure of oxygen at sea level, we would take the total atmospheric pressure, which is in this case 760 millimeters of mercury, and multiply that by the decimal form of 20.9%, which is 0.209. So whenever we are working with percentages, we will always want to use the decimal form of that percentage. So to get the decimal form of a percentage, we take the decimal point in that percentage and move it to the left by 2 spaces. We can do the same for the partial pressure of carbon dioxide at sea level. So we take the total atmospheric pressure, which again at sea level is still 760 millimeters of mercury, and multiply it by the decimal form of 0.04%, which in this case, the decimal form of 0.04% is 0.0004. And that gives us a partial pressure of carbon dioxide of 0.3 millimeters of mercury at sea level, and a partial pressure of oxygen at sea level of 158.8 millimeters of mercury. Although in table 22.4 above, we see that they've rounded up for the partial pressure of oxygen. They've rounded it up to 159. But the formula here, the calculation, still gives us the number that is correct. So now let's say we were to climb to the top of a high mountain. So for example, the highest mountain on Earth, which is Mount Everest, which is located at the border between Nepal and Tibet. So we find that the total atmospheric pressure on the top of Mount Everest is lower than it is at sea level because there is less atmosphere on top of us the higher in altitude that we go. So we'll see that the atmospheric pressure always decreases as elevation increases. So here I would like to ask you to take a moment to calculate the partial pressure of oxygen if the PATM, or the atmospheric pressure on Mount Everest, is 226 millimeters of mercury. So just like with the previous problems, we would calculate the partial pressure of oxygen by taking the total atmospheric pressure, which in this case is 226 millimeters of mercury, and multiplying it by the decimal form of 20.9%, since oxygen gas at the summit of Mount Everest still makes up 20.9% of Earth's atmosphere. So we would multiply that 226 millimeters of mercury by 0.209. And in this case, the partial pressure of oxygen on the summit of Mount Everest is approximately 47 millimeters of mercury. So keep in mind that gas diffuses from high pressure to low pressure. So if the partial pressure of oxygen is lower, oxygen will not diffuse as easily into your blood. This is often why bottled oxygen is needed when climbing high elevations. That supplemental oxygen helps to increase the partial pressure of oxygen gas and makes it easier for that gas to diffuse into our bloodstream. So since oxygen diffuses into the bloodstream, having a high partial pressure of oxygen in the air that we breathe is going to be critical for its ability to diffuse into the blood. So the partial pressure of oxygen in the air we breathe must be higher than the partial pressure of oxygen in the blood of the pulmonary capillaries. So we see that the partial pressure of oxygen in the air that is within the alveoli at sea level is typically around 104 millimeters of mercury. So notice it's a little lower than the partial pressure of 158 millimeters of mercury of oxygen at sea level that we calculated earlier. Because remember that when we exhale, some of the air remains in our lungs to keep the alveoli inflated, and that air often contains very little oxygen. So therefore, fresh air that's being brought in with each inhalation is mixing with old air that has very little oxygen in it. So as a result, we get a slight decrease in the partial pressure of oxygen in the alveoli. So blood in the arterioles that is making its way to the pulmonary capillaries has a partial pressure of oxygen of about 40 millimeters of mercury. So because we see that the partial pressure of oxygen is higher in the air in the alveoli and lower in the arterial blood that's being delivered to the pulmonary capillaries, we see that oxygen will diffuse from the air in the alveoli into the pulmonary capillaries. It's always diffusing high to low. So we see that it is the difference in partial pressure of oxygen that drives oxygen diffusion from the alveoli to the pulmonary capillaries. So we also see that at the pulmonary capillaries, it takes about a quarter of a second, that is 0.25 seconds, for hemoglobin to become saturated with oxygen. However, a single red blood cell takes roughly 3/4 of a second, so that is 0.75 seconds, to travel through the length of a pulmonary capillary. So what does this mean? It ensures that the hemoglobin will still be fully saturated with oxygen even if blood flow through the pulmonary capillaries is increased by 3 times. So to show that visually with this graph, we see that it takes 0.25 seconds for blood oxygen levels in the pulmonary capillaries to reach equilibrium with the alveolar oxygen concentration of 104 millimeters of mercury. So even if blood were moving 3 times faster, hemoglobin would still be fully saturated with oxygen by the time it left the pulmonary capillaries. So why would it be moving faster? We see that it might be moving faster during exercise or during periods of increased physical activity. So we see that the same difference in partial pressures is what causes oxygen to diffuse from the blood into the tissues. So we see that a partial pressure of oxygen in the tissue capillaries, so that is roughly about 100 millimeters of mercury of the partial pressure of oxygen, is higher than the partial pressure of oxygen in the tissues themselves, where we see that the partial pressure of oxygen is less than 40 millimeters of mercury at the tissues where that oxygen is needed. So again, this pressure gradient from high to low is what's causing the oxygen gas to diffuse out of the blood that's in the tissue capillaries and into the tissues themselves. So as we saw with Dalton's law, the higher the total pressure means the higher the partial pressures, even if we don't change the concentration of the gas. Henry's law can be viewed as kind of an extension of Dalton's law in that a gas will dissolve into a liquid like blood in proportion to its partial pressure. So the key takeaways of this law is that the higher partial pressures will lead to better diffusion, and lower partial pressures will lead to lower diffusion into a liquid. So this is applicable because it describes diffusion rates for gases that are in contact with liquids. The lungs apply to this because we see thin layers of water in the alveoli, and we also see water in the blood, both of which are places where oxygen and carbon dioxide must diffuse through if they are to move into or out of the bloodstream. So we see that hyperbaric or high pressure chambers help to drive greater diffusion of oxygen into the blood because these chambers have increased ambient pressures inside of them, which would also increase the partial pressures of gases like oxygen. So we've seen that partial pressures of respiratory gases help to drive diffusion during the process of external respiration. Now let's re-examine the respiratory membrane. So recall that the respiratory membrane in the lungs, that is between the air in the alveoli and the blood that's flowing through the pulmonary capillaries, is extremely thin. It's approximately 0.5 micrometers in diameter, which is roughly 14 times thinner than the diameter of a typical erythrocyte. So not only do we see that the respiratory membrane is very thin, but it also has an extremely high surface area thanks to the many millions of alveoli that are within each lung. So the combination of being very thin along with a high surface area is an extremely ideal combination to promote diffusion. The effective thickness of the respiratory membrane increases dramatically if the lungs become waterlogged or they encounter tissue edema. So waterlogging can occur during conditions like pneumonia. As the thickness of the membrane increases, diffusion dramatically increases, which means that waterlogged lungs would suffer from extremely poor gas exchange, creating situations of oxygen deprivation throughout the body. We also see that conditions like emphysema, which is a condition that destroys alveolar surface area, would also compromise gas exchange and could also create situations of oxygen deprivation. So finally, let's examine the phenomenon of ventilation-perfusion coupling. So ventilation is the amount of gas that's reaching the alveoli, while perfusion describes the blood flow through the alveolar capillaries. So you can think of perfusion as the amount of blood that's reaching the alveolar capillaries at any given time. So optimal gas exchange is extremely dependent on a match between ventilation and perfusion. So hence the term ventilation-perfusion coupling. So let's examine how this works. So we see that if ventilation is less than perfusion, so that is, if ventilation is too low or perfusion is too high and there is a mismatch, this is going to cause a decrease in the partial pressure of oxygen in the alveoli and an increase in the partial pressure of carbon dioxide within the alveoli. We see that what will happen is that our arterial diameter will be reduced, which is going to decrease perfusion and helps to bring a match to both perfusion and ventilation. On the other hand, if ventilation is too high or perfusion is too low and there is a mismatch, this causes an increase in the partial pressure of oxygen that is in the alveoli, and it creates a decrease in the partial pressure of carbon dioxide, also within those alveoli. So we see that arterial diameter is increased, which increases perfusion through the pulmonary capillaries and brings a better match to ventilation-perfusion coupling.